So this is a presentation of a project that Kenny spearheaded. It's T1234, and you will learn what this is. It's basically a T1-weighted EPI that has much more flexibility to do both functional and anatomical scanning, and we are pitching it today as a substitute for MP2 And I think Kenny has one slide, if you come around, for your motivation of why you're doing this, and then I will also do, he asked me to do most of the talking later. Yeah.
Okay, basically, just for people that don't know me, I work for Peter in NH here as an MRI tech. As a tech, a lot of time we see people running out of time because the high resolution MP range take about 10 minutes. And when people running out of time, they either shorten their test or don't do the MP range at all at the end. Or some people may reduce the time on the MP range, but it's very difficult because if you reduce the number of slices, the TI time, and also the sequence itself is a flash base. So, and also for the 3D sequence to reduce the slices, you also encounter the phase flap problem on the phase direction. So basically, the motivation for me to do this one is Renzo and I try to find a sequence that is compatible contrast with MP range, but with a much shorter time. And this is my first motivation on this one here. So the second thing is personally, I like MR physics, especially for the Fourier transform and how the data fill in the K-space, the MX and MC plane, the signal coming from there, that's really intrigues me. And since Renzo gave me a chance to work on this project, I'm have a chance to play with the KP. If people not familiar with this, this is the full name stand for is controlled aliasing in parallel imaging results in high resolution. This is a new way to acquire the 3D data with very high acceleration. So that is the reason for me is irresistible to join this project with Renzo. And the last thing is the last project I worked in here is working with Jersey in 2009, working with his project on neurofeedback. Since he left in 2009 to Tulsa, Oklahoma, I haven't had any chance to work on the project. So since now Renzo is come on board, I hope we have more chance to work on some method development for the core or for the facility. So this way, I will have more chance to learn and work on the new thing, especially with Renzo. Okay, this is all my personal perspective about working on this project. So since Renzo is much better than me on the technical side, so without further ado, I let him present our findings.
Right, thanks, Kenny. So to motivate it from my perspective, as part of the ISMREM study group on brain function, we had a survey on what is the most limiting thing in layer-dependent fMRI. And to my huge surprise, it's not sensitivity. People don't care about sensitivity. What the most limiting thing is people say they are limited about registration quality, which was a surprise for me. And maybe it shouldn't have been a surprise if you consider that people spend a lot of time acquiring good anatomical reference data, 10 minutes for an MP2 range, or 9 to 10 minutes, which is double the time you usually spend at 3 Tesla for these standard MP ranges. So 7 Tesla should give us more, but still it's so hard. And then it's a different distortion, different contrast, so it's hard to register. And maybe the most personal motivation why I want to work on anything whole brain 3D EPI is because since like 4 or 5 years, I'm really investing a lot of effort to get whole brain EPI working with mixed success. Like, I think we were successful in the sense that we could convince the field that there is signal to harvest. We don't really know how stable it is. There is a lot of potential, we convinced that, but still it's hard, specifically if you look at the bottom 60% of the brain, which is usually not looked at in layer-dependent fMRI. And that's not a new problem. That's a problem since the advent of 7 Tesla fMRI, MRI for that matter. And I know that Sam and Andrew had successes there, but still it's hard. You make compromises, and it's not like vasoactivation maps jump at you like we're used to in other fields. So the reason why whole brain layer fMRI is hard is because of the deep brain structures, and we need new ways of thinking about that. And so I hope working with Kenny on the whole brain EPI will give us a better understanding of the sources or new perspective of the sources of error. Because I just talked about this with Peter in the other meeting, that at the last 2 workshops, it's super easy to find collaborators who want to use layer fMRI and have their very fancy ideas and tasks and paradigms to do exciting stuff between cortical and subcortical things. But it's supposed to be a kind of iterative approach, that we improve the methodology, the acquisition, and then do some applications, are informed about the limits, go back to the acquisition. But the acquisition side is kind of neglected often. It's kind of the boring part. And it's easier to find collaborators who want to apply stuff than collaborators who want to turn their attention to the dirty work in the trenches and figuring out how we deal with those variances.
So Renzo,
yes.
Can I ask a question here? So I'm actually really surprised by that, because I always thought that, to me, the images themselves, I mean, 2 things. One, the images themselves for layer fMRI seem like they would be, especially MT weighted, if we do that, are high enough contrast that you can actually use those as the anatomic references. I mean, it seems like where there's no issue of registration then, it seems that that's the best solution. But then the other thing that has been done for years and years and years is, you could acquire a segmented higher resolution scan, if you, well, depending on what you're using, that just matches the readout window. I mean, it's all of the distortions that people try to do in post-processing for correcting are just due to the readout window length. And if you just match the readout window length of whatever scan you do, then the distortions should be matched, right?
Exactly, and that's the motivation for the project, right? Like, we are not the first one that's doing T1 weighted EPI. In fact, I think since the advent of Vaso EPI, we have always done this because Vaso comes along with the T1 weighting. Though not everybody's doing Vaso, and there are, I think Jonathan Polimeni pitched what you pitched just now, to use a T1 weighted with the exact distortion matched EPI. However, and there are many other groups who did it, but none of them is using it. It's not really robust. And if you want to have, for a single slab, like Witzke van der Zweig, who does do segmentation, matching the readout window, it takes 2 minutes to get a single image, right, with high enough quality. And you can see how kind of high quality there is. If you have a bigger slab, it takes 5 minutes. And then if you want to have even a T1 mapping, it takes 25 minutes for 60 slices. The MT thing is awesome, and Yukoi, I saw him previously, maybe he's there. The MT is a good contrast, a structural contrast. It's comparable to T1 with the macro molecules, though MT is never as efficient as T1, right? MT, you cannot null a given compartment. In the best case, if you're not cell limited, you can maybe have an MT weighting of 60%. So MT, either you average the heck out of it, like Yukoi does. It takes 8 minutes, though, for kind of a slab, a thick slab. Or like Martina Callahan, they are doing it. They don't have as much MT weighting, but then they have a structural reference scans where the contrast doesn't really match. So you can be either fast or you, the contrast to noise ratio efficiency for MT is not as efficient as T1. So therefore, we, at T1, you have the entire ratio from minus equilibrium to plus equilibrium magnetization available, so you can optimize your contrast to noise for gray matter and white matter. Whereas in MT, you have kind of maybe 25% of that dynamic range. So we are starting from kind of a sequence like that, where we have a 3D EPI, and we want to basically turn all the knobs that we have available after the upgrades of the 7 Tesla to optimize this for structural reference imaging, which is, exactly what you said. And it's weird why nobody is doing it so far. And I think it's just not, go ahead.
Yeah, I mean, that's weird because, just sorry to interrupt, but I mean, it's especially weird because I actually think that the registration with post-processing is impossible at this resolution. It's just impossible, and so it's not even worth trying. I mean, it should be made. That point should be made really strong to the community, because it's just, this is the only way to really do it well. So anyway.
And they know they're limited by it, as we have seen from the survey. So we need a good distortion-matched whole brain T1 weighted scan, and we need to have it robust, and we need to have it fast, and we have a lot of degrees of freedom available, and we want to optimize them to have something that we can give to the users. And the different knobs that we're gonna talk about, that we played around, are those ones. So first is the segmentation. How are we gonna get the best structural contrast with the right distortions that we want? And I think after the upgrade, we have access to these new reconstruction engines, the IcePad, which is much more flexible with respect to segmentation within and across planes, but also we have access to new sequence code, like the bond sequence, which in turn gives us more flexibility there. And I would like to motivate the kind of thinking about segmentation with this lifeguard metaphor, where we have the lifeguard who needs to serve the person in distress, and direct way to rush there would be Euclidean distance the shortest, but then the lifeguard spends a lot of time in dangerous waters, and the lifeguard is not as fast in these waters, right? And maybe it would be more efficient to spend as much as time on the beach and then be in the water as little as possible. And I think this is here metaphorically speaking for the EPI versus flash, where in the EPI we have very little time outside actually acquiring data. We just have the excitation pulse, our navigators, and spend most of the time in dangerous waters. And they are dangerous because as long as the ADCs are open and we're going through k-space, any kind of phase errors accumulate. And at 7 Tesla, the timescales are just faster. And therefore, a lot of errors occur, and we end up with EPI issues. And the other extreme, which people consider as structural imaging, is the opposite, where we spend a little amount actually sampling the data. We spend most of the time on acquisition and magnetization preparation and so on. So we know from high school physics, maybe you had these math problems, that something in between might be the most efficient way. And if you look at the history of the last decade in what are the innovations in the sequence domain for high resolution imaging, I think all of them, literally all of them, or these methods that are out there, are kind of advanced combination of acceleration and segmentation. And this is like EPIC or EPTI or short selective CAIPI, and few of them caught on so far, mostly I think because of the applicability issues, that it needs to be robust and needs to reconstruct on the scanner. You don't want to tell users to export raw data and do everything offline. So to turn this knob, we basically acquired for fun here one segment, and with a sagittal plane we have huge matrix sizes of 250 and more. So echo times is forever. We have all these issues. Nobody would do fMRI like that. If you have 2 segments, it kind of looks better. 4 segments is already kind of definitely better than what we're used to with fMRI. And if we increase this further and further and further, you can see that it's kind of non-linear, that already after 7 segments or 14 segments, it looks quite nice, almost like as identical as an MP2 range, which has 240 segments, one shot, one line, right? And what I also want to notice there for a thin slab, for example, the timing is not linear, right? So going from 1 segment to 2 segments means that we have double the number of segments, but the segments are only half as long. So it's the time it requires to get the full k-space is a bit longer, but it's not double because the segments are shorter. So images for this project now, where we want to have a good T1 weighted reference scans, is either 7 segments or 14 segments. We were conservative, so we run with 40 segments, which is still like a factor of 20 or 15 faster than MP2 range. The sequence that Kenny simulated up and down is shown here, just to give you a quick overview. This is a sequence diagram where we have the top row, the RF. The second row is the read gradient, X gradient. Then we have Y, which are the blips. And then the phase encoding is in the Z direction. We have a sagittal protocol. So we have multiple partitions. In fact, we have 14, as I just showed you. And we have 2 TRs here. This would be 1 TR, and this would be 1 TR. When you look into one of those partitions, you basically see that we're going through k-space sparsely, but we're going through k-space twice. So we have 2 inversion times. And if you look at each one of those segments, you can see it's a little EPI readout. So we have a water excitation, binomial 1-1 water excitation as implemented from Rüdi. We have our phase encoding blips. We have a Kuiper blips that I will talk about. We were quite generous with respect to the crushers because we have body gradients and they are bulky and they have peripheral nerve stimulation issues. So we are basically wasting 20% of the time to get the peripheral nerve stimulation, which is modeled down there, and down to a low level so we can start again. Because ultimately we are limited with peripheral nerve stimulation at the shoulders. We're not limited by the gradient performance. To have a full control of what to expect with this kind of looping structure, Kenny wrote a Bloch solver, which is an understatement. I think you have 20 scripts I saw day before yesterday altogether, simulating all the looping structure in that sequence where he basically has the third Bloch equation, the relaxation in the Z direction, with the increments for a given T1 and then an array of flip angles, which we then optimize. So here you see the same thing from the MZ magnetization for the sequence that we just looked at, where we have inversion relaxation, but you see we have kind of two partitions. So those are the two TRs, because Kenny was worried that just having one TR, we are not in steady state yet, so he simulates several of those to go into a steady state. To also account for the magnetization loss from the previous TRs. And then here you see the Z magnetization for gray matter and white matter for these two inversion times. And what you can see is that we have different effective T1 relaxation. So each, like the lines here are basically consisting of all these sawtooth patterns because we have flip angles that we shoot for the excitation of the individual partitions. So we are actually in control of our T1. We don't see T1 here as a tissue type parameter, but basically we don't allow the magnetization to relax freely, but we continuously manipulate it to maintain a certain dynamic equilibrium and steady state for gray matter and white matter, and then we can actually optimize this, as I will show you in a second. If you are interested more in the transverse plane, you can see how with the larger flip angles, even though we have less Z magnetization, we actually have more signal available, and we can optimize that. The use and why I was so excited that Kenny did all this simulation work was because we can really optimize our flip angle distribution based on any features that we want. So in this specific application, we were interested in gray matter, white matter, contrast to noise ratio, but you can also then export this for vaso, for blood volume sensitivity, or whatever you like. To not only look at TSNR, but basically contrast to noise ratio. We want to invert this model to actually then, while we are scanning fMRI, also get T1 values in physical units of milliseconds, and also we want to have artifact hunting because we want to have smooth transitions. And Kenny talked about Kuiper, so I want to quickly show how this relaxation is then used to fill in K-space, unless Kenny has anything to comment here.
So as what to say about that, this basically we're using the MATLAB tracking millisecond to millisecond how the signal change on MC and MX plane. So if you can see, because we have a two flip angle, you can see the dip between two inversion poles. There's a little dip over there. And also the magnify on the right upper corner, you can see the MC coming up and coming down, coming up and coming down. That is because the flip angle, we are putting each in each inversion pose, we put about 124 flip angle over there. So that is the small angle over there. There's a 124 small angle up there.
Right. So here we fill our K-space. This is a graphic that Kenny generated. We have the entire K-space here with 250 slices. We have two dimensions. So the left-right dimension is the KYT space. However, here we also have an additional dimension, namely the KZ-TI space. And the different color coding refers to the sampling scheme that we use at the end. So the red one would be the first partition. So basically we go into the direction of your screen here, then we have a partition of like a EPI factor of 14, come out here again, and you can see it's not the same line, so we do blipped Kuiper within the partitions, but then for the different segments we do a skipped Kuiper. So here you have two consecutive shots within two consecutive lines within the same shot with blipped Kuiper, and then here after you acquired all the 14 lines and your at the end of one side of K-space, you have the next shot and jump 3. So all the lines that, or the fields that are colorful means those fields are acquired. The other ones are subsampled with grappa then. And you can see we have this KP shifting, basically doing a KY shift, like a pre-phased KP for the individual partitions, but then a blipped KP within each partition to have a nice regular distribution. So basically we have the consecutive shots then in the different colors. So after all the red lines are acquired, we go back in the next inversion recovery and acquire the orange ones and so on for different inversion recoveries. So we have 2 degrees of freedom gained by that. First is that with the partition in plane, we can really uncouple the artifact level from our matrix size, which is relevant. So basically we are in control of our phase errors, which are so limiting in the deep brain structure. But secondly, we can also uncouple the inversion times from the number of partitions you have, which, for example, is not usable in MP2 where you very often have these dead times in there, and very often you cannot choose the inversion time that you want to have for a given matrix size. So we basically have this additional degree of freedom. And to make things a bit more complicated, we actually have 2 K-spaces that we acquire. So we have all the red lines in one inversion time, have all the red lines of the other inversion time, and then go back to the first K-space, fill it, interleave the orange ones, and so on. Is there anything you want to say, Kenny?
Yeah. Just give you a little bit context about the number over there. You can see 117, 37, 3473, all this number. This is the time sequence. For example, when we acquire the data, we acquire the number 1 first and then jump to the column 15, the number 2, and then we go to another one is at 29 because out of the page over there. So this is basically the timing number. The number that at the time that we acquire the data on the K-space, on the KC and KY plane. The whole, each page, because you see there's a 2 page of K-space over there. Each page of K-space, there's about 1,200 data points over there. And that means the total, the first TI and second TI altogether is 2,400. For each K-space, each page, if you consider, because we have the KX go inside the page inside there, since the resolution is 232, so you are thinking about each K-space, each page is about almost 3 million data points over there. So altogether with 2 flip angle, our data points are about 6 million over there. Okay.
Many data points.
Yeah, a lot of data points, yes. It's
so
massive.
We skip this. The next knob we turned is the PTX, which was maybe a bit frustrating. And maybe some of you have maybe seen this slide already. So we got the Pasteur package from Paris, the universal pulses, which really looks awesome. They are KT points pulses. So we know that we have the issues in the deep brain structures, and universal pulses or PTX can solve that. However, when in the same participant we do it as a next scan, our scan, with our sequence, it doesn't really help so much. So the frustration here is that the universal pulses are really benefiting from the KT points. We have gradients during the excitations, and you cannot really do KT points without PTX. So it's the PTX that makes the KT points usable, but it's not the PTX that makes these images look nice and homogeneous. It's more the KT points. So if you don't have the KT points in your sequence, it doesn't really buy you that much, the PTX, which was kind of frustrating because it was trouble to get it to work, especially after the bias field correction. There's almost no difference. We know that the PTX coil is slightly bigger, but so far we are not really convinced that this buys us as much with respect to coverage anyway. They're probably just bigger because there's more electronics in there. The active elements, that the loops are, it's not clear if they are bigger. I know that Natalia has a CT scan. She could not really confirm that they are bigger, though Gael from Lani's group is saying that the coverage should be bigger even when you run the PTX coil in CP mode. We were a lot worried about shear factor penalties because we know already from previous scans that the uncoupling is harder of the receive side if you have more transmit channels. For the moderate Grappa acceleration that we are using here, we did not see that. So it doesn't really matter if you're doing it at PTX or STX. So ultimately, the frustrating thing with PTX is, even though now it's usable and we have this additional knob to turn, it doesn't really bias that much. It's the top of the brain that's in the center of the coil. So down there, we're basically out the coil anyway. And we have these vertical arrangements of the elements. So we don't have any degree of freedom from the hardware side to push down the B1 plus. So you can run it in PTX. Maybe you gain a bit, but not much. The next knob that we turned is the read and the phase directions, which I want to show here for this protocol that we are proposing. It's 3 to 4 minutes. And so we have a T1 weighted scan. We have 2 inversions, as I said. We have a 3D EPI readout, and we want to use 4 directions. So we want to be in full control of the distortions, but also these fuzzy ripples that you might remember from my ISMRAM talk. So we are switching back the read direction and the phase direction. And maybe you remember that we have these low frequency shadings without actual geometric distortions, which we can account for with the dual polarity read, because the ghosting artifact where this is coming from is exactly opposite in the complex value domain. And then on top of that, even with 14 segments, we do have some geometric distortions in some areas. So we also want to control that and actually amplify that in the reconstruction to match it with the functional scan. So we have 4 complete images. That's where the 4 is coming from. And it takes 3 to 4 minutes. Actually, it's like 4 sets of images. So we have 2 inversions for each of the 4 contrasts, and we need to do it in magnitude and phase in order to account for the fuzzy ripples in complex value domain, but also for the distortion correction if we want to do it in k-space, which you don't need to, of course. So we have actually 8 sets of complex valued images that we acquire within 3 minutes, 40 seconds to get one uni image that looks like an MP2 range. And because we are in control of the distortions, you can basically have an additional knob to choose any distortions that you want on the reconstruction side, but you can also adjust it based on the segmentation and the effective echo spacing on the acquisition side if you want. For example, so when we use the most often used protocol, I think that's used at 7 Tesla, it's a multi-band protocol from the UK 7T project, which is popular also here for some studies. It's 1.5 millimeter. You see that the bolt scan looks like that. And then if you want to get that to an MP2 range at reasonable accuracy, not even speaking about layers, is hard because you have different contrasts and you have different geometric distortions. So this is, as a bridge, to build that bridge, the T1234 can come in, where we have the same T2 star weighting with the same geometric distortions. And then from the same data that we used to get those T1234, we also get a uni image, which must have the same distortion. It is literally in the same space. It's coming from the same data. And then we have the same T1 contrast that you can match it to the MP2 range. If you still want to use the MP2 range, you can actually run FreeSurf or anything directly in this space too, as I will show you. The next thing that we wanted to optimize is the flip angles, because in MP2 range, usually we are under flipping, but this is needed even though it makes it less efficient for the quantifiability. So Kenny has the entire Bloch model of that sequence. So we could basically optimize the gray matter white matter contrast, where we have the gray matter contrast and the white matter difference for the 2 different inversion times, which we want to maximize. But actually, we not only want to maximize it, but we want to maximize it while also making sure that we are minimizing noise. So for example, we actually have the best contrast to noise ratio if we make gray matter 0, just acquiring the image while gray matter is nulled. But then we have a lot of 0 and a lot of noise, so we want to minimize the noise, which is why we generated this equation following the Gaussian propagation of uncertainty. And then you can look at the contrast to noise ratio for gray matter and white matter as a function of your 2 flip angles for the different inversion times. And maybe Kenny made this little movie here where you can see, I'm screen recording, that's why it's lagging. You can see that we have this very nice plateau for the flip angle 2. The flip angle 1 is more sensitive. The red point is referring to the optimum. Right, and to make sure that our model is right and also kind of to optimize it until we got the model right and calibrated, you can see that you can either have bad contrast and bad SNR. You can have a good SNR but not so great contrast, or you can have good contrast and bad SNR, and then in the optimum, the red point would be somewhere over there, which is not the same as MP2 range, because we basically want to solve the quantification by other means. Is there anything you want to say?
Yeah, I just want to add some context about the equation over there. The gray matter, the T1 and T2 value over there, basically we are, since we have about 62 TR for each TI inversion, so basically we find individually each TR, the gray matter and the white matter between the inversion, and then we average everything together. So this is basically the average value for all the signal noise ratio over there. Not individual point, is the whole 3D volume, the average. Yeah.
Right, let's look at the quantification then, where we can basically invert this. So Kenny generated a lookup table where we predict the ratio of the signal for the first and the second inversion time as a function of T1 and as a function of the flip angle, because we know that the flip angle is not homogeneous in space, so we need to account for that. And then as soon as we have this lookup table, we can actually invert it and see, okay, this is what we measured. The flip angle is something that we can assume based on our nominal flip angle, and the distribution is actually almost identical across people, the idea of the universal pulses. If you really, really care about it, you can actually also acquire a field map, which we didn't. The ratio is the thing that we measured, so then we can use the lookup table to calculate the T1s based on that, while optimizing contrast to noise ratio. And right. And this is also a little video that Kenny generated, because in this table, you cannot really see that the columns are going negative on the other direction. So the 2 points here, maybe you can see them, are the gray matter and white matter, where you can see we are on this hyperplane, and dependent on the kind of flip angle that we are using, you can separate those 2 points further or less. We don't want to go to too small flip angles on the kind of right side here, even though we have a larger contrast, but there we also have larger noise. So the 2 points are the ones with the best contrast to noise ratio. Anything to add?
Yeah. About the bar graph over there, basically, since we are based on the contrast noise ratio, the equation, we found out the optimum flip angle is 11 and 15 over there. So basically, on the x-axis for the bar graph, we are scaling from 0.3 to 2 with the increments of 5% for each one. So you can see starting from 3.3 and 4.5 flip angle to until 22 degrees to 30 degrees. So basically, on the right side, the y-axis, we put a different T1 value over there from 800 millisecond to 2,800 millisecond. So we plug this information to the block equation and compare the signal between the first TI and second TI and generate the map. So the second thing I want to show is that if you look at the bar graph of the left upper end, you can see the area seems flat. So basically, that is the zero. The ratio is a 0 over there. So that is the flat. What it means is all the bar over there is going downwards, the negative value over there. So this is the one I really want to point out there.
Which is also the reason why we need the complex value, right? We need the phase, because you can, we need to know in which direction the magnetization points.
And also the video so people know that where's the negative going to.
Right.
Yeah.
So the T1 values that you get with this make sense. We have a nice white matter peak and a gray matter peak. So you can use it for whatever reason you might want to have quantification. For example, if you want to use it as a marker of inflammation, whatever, it's quantitative. Let's use it also for functional mapping, because we basically, it is EPI, so we can do functional mapping of T1. So for example, when you trade off the coverage, then with acquisition, you can easily get multiple inversion times with variable sensitivity of a T1 weighting. So for example, for the first inversion time, where CSF here is still negative, gray matter is almost crossing to 0, we have a huge T1 weighting, especially in the complex value domain. We have a medium T to star weighting that is identical for all the readouts. And then for the next inversion time, we have a weaker T1 weighting or no T1 weighting at the equilibrium later. So we can basically simultaneously estimate T to star and pure T1 changes by like synthesizing a uni image in this way. And if you show this with the flickering checkerboard, you can see that for the T1, like for the shortest inversion time, we have this increase, this functional increase of the quantitative T1, which kind of counteracts the bold signal change. So we actually have a functional signal increase, even though like increase during the rest periods. So the T2 star weighting is shown here. This would be a clean bold where you have the T2 star increase, signal increase, whereas for the, like, if you have more T1 weighting, this is counteracted. And for the uni image, which is then in units of R1, you can see that the signal goes down. So we have a quantitative T1 increase during activation increase, simultaneously as measuring the T2 star with this model of doing simultaneous like T1 and like EPI, because we have this, these two separate orthogonal directions of the KYT space and the KCTI space, which I think makes sense that the T1 increases because this is, I think, the same contrast mechanism as VASO, so that you have more long T1 components in your voxel, you have more blood in there. It is still kind of noisier compared to what we would expect from a like T2 star weighted. Okay, these are all the knobs we turned. So now we wanted to see if it's useful. We tested this on all 3 7 Tesla scanners across many participants. There's also a test-retest animation somewhere, maybe this one. So it works across head sizes and everything to quantify the stability. We also did kind of test-retests where we looked at the standard deviation of the test-retest versus the mean, and we see that we have about 2% variance across test-retest. It's literally a measure of TSNR for structural imaging. How deep can we go? Because we do this uni image model as an MP2 range, we are not directly as sensitive to the deep brain structure. So you can see the gray matter, white matter in the spine. Here I'm showing you the difference between the PTX and STX, where maybe the PTX helps you a bit down there, not too much though. One thing that I definitely want to highlight is the motion, because if you run a 10 minutes MP2 range with 0.8 millimeters, people move, right? It's very hard to lie still at this resolution. So very often we have these kind of wiggly artifacts. This is not the best participants that we have, and we actually invited her because we knew that she moves a bit. And when you do the same thing now for the T1234, you can see that we have the 4 images, and you can see that she moves a bit, but the most critical thing is the within TR motion, right? Some TRs are just bad. For the TR to TR motion, we can account for this retrospectively by doing standard motion correction, and then we can censor the time points where the motion is bad. So in MP2 range, you cannot do that, right? If they move at one time during the entire MP2 range, your data look crappy. For the T1234, we are not having this issue. And even when she moves a lot, we can still get good maps from the data where she didn't move. Looking at how helpful this can be for standard segmentation while working in the distorted space, I pushed it through like the SPM segmentation, the free surface segmentation, and the FSL fast, or what it's called. And so far, we didn't have any issues. I didn't really, like, of course, you will always find an area where segmentation is not perfect, as you will do for MP2 range, but we didn't do a quantitative comparison of how much longer you need to, or shorter you need to do manual corrections. You definitely don't have the issue with the registration instead. So far, free surface just worked perfectly fine. With respect to speed, I said we have 3 minutes, 40 seconds, and I think we can make it down to 3 minutes if we optimize the crusher, as I talked. If you have just 1 image, it's noisy, and FreeSurfer will not like it. If you have 2 images, it's kind of okay. Manually, like visually, it looks good enough, but I think FreeSurfer likes having better SNR, having the four averages with all the 4 directions. So as a summary, we have 0.8 millimeter whole brain in 3 minutes, 40 seconds. The effective matrix size is 250. We are using a partial Fourier of a bit more than 6/8. This is something that Kenny found out that is not exactly 6/8, because we have 14 partitions, which also means that we have an EPI factor of 14. So because 198 is exactly the 14 squared, more or less coincidence, but since it's not divisible by 14 with the 6/8 partial Fourier, we basically have partitions where we only have 13 ADCs. In order to make the to have a smooth transition of the T1 weighting in K-space. This means that we still need to wait for the time, even though we don't acquire the data, which is kind of wasteful. But we definitely want to have the T2 star issues in one dimension and the T1 issues in the other dimensions. And both of them in EPI result in blurring and issues, but we need to keep them orthogonal. Otherwise, we run into all the issues that people have with like 2D grays, for example. So we have sometimes a line where the ADCs is off. It's a bit wasteful. Those are the optimal flip angles for that protocol. We have very short echo times. So if you want to make this multi-echo, that's absolutely doable, and the sequence allows that. The full protocol is here. Sorry, you want to add anything?
Basically, I just want to collaborate about the grapper tree over there on the screen. Basically, the tree is coming from the slide direction. For the phase direction, the grapper, there's no acceleration on the phase direction. And for the carpet offset, it's 1. So based on those information, you can fill up the K-spaces like the one in color K-space, color block over there on the right lower corner.
All right, so we optimized a lot of knobs. I think it helped. We have something that works for good gray matter, white matter contrast in almost 4 minutes. It's really like the purpose is to be a structural reference for layer-fMRI analyses. It's on all scanners available. All the images in complex valued images are being done and performed at the scanner directly. This includes the coil combination, because it's not trivial to get good phase information. So we're using this the virtual reference coil way of how you can do it in Siemens, kind of the pre-scan normalized without having a body coil at 7 Tesla. So what I want to say is no offline recon necessary. You need to do the pre-processing. For example, you might want to do the retrospective motion correction simply because you can. And you will need to combine all the 3 images, which is straightforward. And we want to submit this to ISMREM. So any suggestions are welcome. But before I ask for your suggestions, I want to thank specifically Marcella. She went out of her way to really make it possible to get us the participants, because the core does not have postbacks. So it's not trivial with the assignments and all. Like, I'm not allowed to write Chris notes. Kenny did that for me. Marcella got the LBC stuff working, and she invested a lot of time there because there was no system before I arrived. So she did the trainings, did everything, and I'm really thankful to her. I want to thank Rüdiger Stirnberg for providing the sequence code so we could have access to all the different looping structure, and we got a lot of help structurally and institutionally for many people. Looking forward to questions. Thank you.
The one thing I want to add is basically, I forget to say about that, is the this protocol, as we saw in the last second slide, is about the grapher factor of flip based on our parameters over there. So in the future, if you change whatever parameters on your protocol, for example, the segmentation number or the resolution, and then you can see how the K-space filling in the sequence on the scanner interface. Because if you go to the special card, as I remember, it's under the special, you can see how the K-space filling on the K-space, how the point is filling over there.